Mr. TG. This is your last video of lesson 8.3 on rational functions. In this last video, we're going to discuss how to graph special situations that might come up. Now, on the first example you're looking at, we're going to graph y equals 3x plus 5 over x minus 2. The one thing you can do with this, if you opt to do this, is if you check it out and you see that you have two binomials, two two-termed expressions, and both numerator and denominator have the same degree, you can transform this equation into something that's maybe more familiar and hopefully more familiar and a little bit easier to graph. And here's how we do that. We simply take the denominator and long divide it into the numerator, okay? Just like you would do if these were whole numbers. I mean, face the fact, if this were 10 over 3, you would just simply divide 3 into 10, right? To change it to a mixed number. And I'll use that as a reference to give us an idea what to do here. So now, but you never actually have divided this out, but what we do is we look at the first terms only. Just focus your attention on that and think of that as 3x divided by x. And the x's cancel. So x goes into 3x 3 times. Then, like when we divide, we get 3. Then we multiply to get the bottom number, 9. 3 times 3 is 9. So 3 times x is 3x. And 3, we got to make sure we multiply it also by a negative 2. That's one that really causes a lot of problems. You figure out how many x's go into 3x, put that number there. Then you distribute that over both terms to get that. That's how we get the 9 up there. Then we subtract. We're going to subtract, and we make sure we subtract the quantity. And then the x's should cancel out. Now 5 minus a negative x is 11. That becomes our remainder. Up here we got a remainder of 1. So now what we're going to do with that is this. We're going to rewrite this equation. I'm not actually going to graph this equation with you because this is going to turn out just like this, the graphs in 8.2. Y is equal to, now what we do is put, like what we do up here, we take the whole number, which is 3, and the remainder is the numerator. I'm going to write it a little bit differently, though. That's where we get a fraction from. So 11 is our remainder, so we put that on top. X minus 2 goes on the bottom. And then our whole number plus 3 is right here. So it's like 3 1/3 here. Remember, 3 1/3, which is what we have here, is the same as 3 plus 1/3. And we're doing the same thing here, only we're dealing with polynomials. So now, if you look at this form now that it's in the exact same form that they were in lesson 8.2. You know the asymptotes, the vertical asymptotes at x equals 2, the horizontal ones at x equals 3, and you can graph the parent function of y equals 11 over x. And I think most of you know how to do that, hopefully, by now. So I'm not going to demonstrate that. If you need more help with that, revert back to that video from section 8.2. So that's one special situation. Remember, both are binomials, both have a degree of 1. Feel free to divide them out. The division is new for you. You just divide the first terms out. X goes into 3x 3 times. Multiply. This is just like long division. 3 times x is 3x. 3 times minus 2 is minus 6. Then we subtract. This remainder, 5 minus a negative 6 is 11. Turns out to be the numerator in our fraction. Divisor is x minus 2. And then our whole number gets placed on the right side, so it looks like our equations. Now, the last example I want to show you looks like this. And it's a situation that is unique. Now, this is a rational function that's already been factored. Sometimes you do have to factor rational functions, so be prepared for that. But I already factored it to save time. What you'll notice at first, we look at excluded values here. We know that x cannot be 2. Hopefully you know that, because actually negative 2. X cannot be a negative 2 because if I set this equal to 0, x equals a negative 2 is an asymptote. So it appears we have a vertical asymptote, but we don't. And here's why. If you look at the factors in your fraction, x plus 2 and x plus 2 are identical. They can be canceled out completely, leaving us with y equals x minus 6. So all of a sudden we've simplified our equation quite dramatically. And now we end up with a linear equation, y equals x minus 6, where the y-intercept's at -6. This has a slope of 1. So that's exactly what we sketch, a line across our graph. And we connect the dots. Hopefully you remember how to do this. But what we have to be concerned with here is that in the initial function, x could not be a -2. That is what we call a hole. We have to honor the fact that the original function, the original rational function, x could not be a -2. So the definition up here says this: rational function that have a common factor in the numerator and denominator that will have removable discontinuity or a hole in the graph. The hole in this case occurs at -2. Let me write it out a little bit nicer here. Yeah, the hole is going to be at a -2 now. Again, what makes it into a hole is that the x plus 2's cancel out. We get a nice clean equation down here. Y equals x minus 6. And that's linear, so I graphed it. But here's what you have to do next. You have to look where x is at -2 right here. You got to kind of go down, straight down from -2, and put a hole in your graph right there above the -2. Just kind of line it up. We have to, again, honor the fact that x, the input for x, cannot be a -2. So our domain would be all real numbers except -2 if they ask that question, because there's a hole at -2. So look for holes or removable discontinuity anytime your graphs have factors that cancel out in your fractions. So hopefully that made sense. We'll certainly work on this in class together. So do your best to try and understand, and let me know if you have any questions, and thanks for watching.